So thank you for taking the time to do my little survey and watch this video. I'm going to talk about the basics of how magnets work, and we're going to see how you think about magnets before this video and how you think about them afterwards. So let's first dive into what we actually make magnets out of. There's different types of magnetism. What we think about as a magnet is what we actually call ferromagnets. So these are like our regular permanent bar magnets or ferromagnets. They're made out of iron, cobalt, nickel. So there's three elements there that we can make these out of, and of course all their alloys. So if you mix those metals with other metals, those materials may be weakly magnetic or not. We have other things called paramagnets and diamagnets. So these are either weakly attracted or repulsed, but um, for all intents and purposes, like for us in the real world every day, we're not really going to think of these materials as magnets because what these terms really mean is on the atomic level, we'll see some sort of interaction with these materials. But for example, if you look at the diamagnetic material gold, so Ag on our periodic table, typically when we think of gold, we do not think of it as magnetic. And if you put up a bar magnet to it, you probably won't see any reaction out of it. So nothing really is going to happen. So that's why we don't really consider it magnetic in the real world, but scientifically they do have a small attraction on an atomic level. So we're going to use most of the time iron to make up our permanent magnets because it is the most common and cheapest material, and that's Fe on our atomic periodic table. Excuse me. Those are the blue little squares down there. So you have iron, cobalt, and nickel. Cobalt's a little more expensive, and nickel is a little bit more expensive as well, so that's why you typically see iron. So let's go into how they work. So if you have a bar magnet made out of one of those three materials or a mixture of them, they're going to have magnetic field lines. This is kind of how we visualize what the magnetic field is doing. So these magnetic field lines, they go out of the north end and into the south end. So these poles, out of the north pole into the south pole, and they just make big circles. And you can look at what is called the magnetic field line density, so how many lines are in an area, and that sort of illustrates the strength of the magnetic field at that point. So you can see there's tons of lines over here and tons of lines over here. It's going to be really strong here, but if you look here in the middle, there's not really any lines at all in the middle, so you're not really going to have a big attraction. That doesn't mean you're not going to have any attraction, but not a very large one. And also something very interesting, if you take a bar magnet and you break it into 100 pieces, you will actually get 100 little bar magnets. So each have their own north and south pole, and you can stick them right back together. So if you broke this into these 5 pieces, if you can stick all these 5 pieces right back on the end of each other, they will stick there and stay there until you pull them apart again. Obviously, they're not going to be as strong as when it was together, but that does hold true. And you can even do this into 100,000 pieces. You can break these up into even one singular atom on their own, and that one singular atom will still have a north and south pole. So let's kind of take this idea of a bar magnet and apply that to Earth's magnetic poles. So really we can think about Earth as one giant bar magnet. And you can see here, here's what we think of as the North Pole, and here's what we think of as the South Pole. And you can see how this bar magnet kind of looks opposite of what we would think. So when we have a compass that points north, really that the end of that compass is, you can think of the compass as a bar magnet too, and the end that points is actually our North Pole. So that North Pole of our compass is going to be attracted to the South Pole of the Earth, right? So if you're standing right here in Brazil and you use your compass, and north is going to be pointed straight up this way to the South Pole of Earth. And you can see these same magnetic field lines go in or out the north and into the south and all around, and just like our regular bar magnet. So what we typically think of as the North Pole is actually our South Pole, and vice versa down here. So let's kind of look at how that compass actually works. So if you have a needle or something and you can rub a magnet on it, you can magnetize it. So you can do the same thing with a nail, screwdrivers, whatever. We can magnetize that and sort of align these magnetic domains, they call them here. And so once those are aligned, we basically have a little magnet, a temporary magnet, and we have those same field lines again. And if we actually put this on like the surface of water or something that allows it to rotate freely, the end of this needle will actually align with Earth's south pole. So it'll turn into a compass. So that's how all these things work. Um, you can just keep scrolling down and fill out the last part of the survey. It's going to be the same exact test that you took at the beginning, and we can see how your results differ.